Hey, we're up, we're back, we're up, we're back, we're so fucking back. Oh my god, no. We're so back. Bro, I was supposed to start this stream like a while ago, but like I've literally just been trying to build a thumbnail for the thing, so alright, so I'm trying to find inspiration, you know. I had a talk with my professor yesterday, trying to do some stuff, and me being the technical person that I am, you know, I think we came to the conclusion that like my skills could be better used in like I don't know, a computationally driven project. So that gave me an idea. I was like, okay, let's see what papers we have that we can read or like save to read to get inspiration for stuff. Now the thing is, I don't know if I am allowed to browse like nature journals and then like stream it while I'm doing it. I mean, I guess it's okay as long as it's open to like it's public access. Provided you are the copyright holder. Okay, instead of going to a journal, let's probably just find something in an archive, right? At least just for the stream. I'm probably gonna like check nature offline. Let's see. Not okay. Alright, let's go to archive, bro. I don't wanna do archive. Archive. I haven't really checked archive as a journal for my field because like I remember last time I talked to my undergrad professor. I think he said something along the lines that it's low key kind of not embarrassing, but you're not really going to be taken seriously if you as a chemist, which I was at the time, I mean I still am, but I'm a biochemist, right? Like you're not going to be taken, your paper's not going to be taken seriously if you publish it on archive. So I don't know. Let's see. Let's hopefully find something. You got physics, mathematics, computer science, quantitative biology, statistics, engineering. I mean, definitely not my forte. All of these. I mean, quantitative biology, probably. Let's see. QBio. Biomolecules, DNA, RNA, protein. Sounds like my corner because I do study peptides. Let's see, other quantitative biology. Work in quantitative biology that does not fit in the other QBio classifications. Quantitative methods, subcellular processes. Nope. Tissues and organs. Nope. All right, so it looks like we're gonna be here. All right. Let's see. Okay, so this is published. Oh, today. Okay. Damn. Adapting evidential neural networks to test time neighbor fusion improves molecular property prediction. Okay, molecular property prediction. Can I use? I mean, I am about to be doing some ML work. Let's see. Okay, transferable implicit solvent machine learning potential for drugs and proteins approaching ab initio accuracy. Ab initio. Why does that not ring a bell? What does that mean? Ab initio is a Latin phrase that shows, okay, from beginning, okay, from inception. So let's read this then. Okay, so transferable implicit solvent. Okay, transferable implicit solvent machine learning potential for drugs and proteins approaching ab initio accuracy. Why don't I understand this? Transferable implicit solvent machine learning potential for drugs and proteins approaching ab initio accuracy. I was about to say concurrency for the moderation. Transferable implicit solvent machine learning potential for drugs and proteins that are approaching ab initio accuracy. What does this mean? All right, okay. I want to read this out of spite because I don't I don't understand this. Like this is a very simple and easy to understand title. This is pissing me off. All right, enhanced diffusion of colloidal tracers due to enzymatic activity. Nah. An all-atom foundation model for microcycle structure prediction and design. Macrocycles. What's a macrocycle? A cyclic molecule or ion containing a ring of 12 or more atoms. Wait, so like 12 in the ring, or like? Okay, yeah, I'm not. No, where are you? Come here. Let's see this. Macrocycles are an emerging and largely underexploited part of chemical space where potential drugs for difficult genomic targets can be discovered. Macrocycles can have advantages over natural twins, such as, okay, but this doesn't tell me what macrocycles are. All right, okay, so macrocycles have been defined as ring systems, all right, consisting of 12 or more atoms. Ring systems with 12 or more atoms. I need to see an example. need an example of a molecule that's a macrocycle. What the hell? This is not, no. Okay. So bro, I mean, I guess like this has to, this should be correct. So let's open this image. Come on, man. Bro, all right, let's zoom in. All right, so 1 2 3 4 5 6 7 8 9 10 11 12. All right, cool. So this is 2 times 5 10 11 12 13 14 15. All right, so this is 12 plus 18. Okay. All right, I see it. So like at least the wow, should I conclude that this has to be in a ring? I'm guessing like the ring has to have at least 12 like the ring itself, not just like the side chains or whatever, side groups that you're trying to. Okay, all right, so anyway, back to archive. An all-atom foundation model for microcycle structure prediction and design. Okay, so this sounds interesting. You know what? I think I'm gonna read this. I'm going to read this. Adapting evidential neural networks to test time neighbor fusion improves molecular property prediction. Yeah, I think I'm gonna read this. Screwed. Well, I take that back. Not gonna read this right now. But yeah, let's see. All right, let's which one should we do first? Actually, I'm interested in this one because I've never really worked in microcycles before. Velia 1. Velia. Is this a company or something? This is a company. Oh my god. I was like, there's no way. Like, yeah, I was like, the publishers also own the journals, bro. Velia pioneers computational drug design to create de novo microcycles, entirely new molecules inspired by biology, but designed from first principles through AI-driven methods. All right, born from Nobel Prize-winning research at the Institute of Protein Design. Is this a Baker Lab? Wait, is this from the Baker Lab? Bro, like, I'm getting so sidetracked, but I need to know if this is from the Baker Lab. Let's see. There it is. There it is. There it is. So this is his company. Man, they published a paper. David Baker. Okay. Alright. 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 Okay. Alright. Alright. All right, all right, all right. But I mean, talk about like my God. Velia 1 is a neural network built from first principles. Okay. Specifically tailored to model the structure of macrocycles through diverse chemistries. Alright, it achieves state-of-the-art performance at recapturing a broad range of microcycle structures, more than doubling the performance of the next best method. So the next best method to capture microcycle structures. Okay, boom. Its structural capabilities provide a foundation for many important problems in design, including enriching for permeable compounds and screening for protein binders using energy landscapes. All right, okay, we're definitely reading this paper. We're definitely reading this paper. It's a David Baker paper, so we're definitely, well, it's not a David Baker paper. Is he on it? Wait, where was that again? Oh. Well, I mean, it is his company. I mean, I don't think this went out without him taking a gander at it, especially since it came out today. All right, let's read this. Let's read this. I'm interested. I am interested. Where's my notebook? Okay. All right. Cool. An all-atom foundation for a model. Like, I'm like, I know this is a David Baker paper. I know this is a David Baker paper. Well, not a David Baker paper, but as soon as they mention this, the protein is on. Okay, all right. Macrocyclic peptides. Okay. Are an increasingly important therapeutic modality, but existing computational methods for modeling their structures and properties are limited in scope and do not generalize well across the synthetically accessible chemical space. Okay. All right, let's reread that again. Macrocyclic peptides, you know, ring structures that have at least 12. So I'm assuming like it's a peptide, it's a ring peptide with at least 12 amino acids in them. At least 12. All right, okay, cool. Macrocyclic peptides are an increasingly wait, but how do you even do that? Whatever, we go to that, but the existing computational methods for modeling the structures and properties are limited in scope and do not generalize well across the synthetically accessible chemical space. In this work, we introduce Velia 1, a deep learning model that addresses two central challenges in macrocycle design: sampling biologically relevant conformations across arbitrary chemistries and predicting key developability properties such as membrane permeability. All right, so that's one of the properties they're trying to predict. So if I understand this correctly, right, prior to the invention to the creation of Velia 1, prior to the creation of Velia 1, to go from macrocycle structure to property via a model was very challenging. My gosh, that is such a vague way to think about it, right? Okay, let's see. All right, and they did not generalize well across the synthetically accessible chemical space, right? So it's I'm assuming because of the complexity. So like, here's what I'm thinking, right? Because it's a macrocycle, you have different amino acids, you're definitely gonna have a wide space of properties, right? Almost combinatorial. That's my assumption. Obviously, like, I'm welcome to be corrected at any point in time. But I assume that because of how combinatorially expensive it is to like look at all the possible intramolecular interactions that then define the property, because of that challenge, it's hard. Computational methods prior to the invention of VLU1 were very challenging to develop for this specific task. That's what I'm thinking. Okay. So, in this work, we introduced VLU1, a deep learning model that addresses two central challenges in macrocycle design: sampling biologically relevant conformations across arbitrary chemistries and predicting key developability properties such as membrane permeability. All right, cool. All right, so basically just gonna sample like the important spaces. I wonder how it does that. And then we're able to go from important space that we found here out of like this millions of possible spaces, for example. We go from this specific property to membrane permeability. Okay, cool. VLU1 operates on a uniform all-atom representation and is trained on a heterogeneous structural datasets spanning diverse topologies and chemical classes. Okay. Across a broad set of macrocycles composed of canonical and non-canonical residues. Alright, VLU1 substantially improves geometric accuracy relative to physics-based methods. Okay, so this model improves the geometric accuracy. Like I'm assuming what they're trying to say. Like it generalizes the conformation well. Is this AlphaFold but for macrocycles? Is that what I'm hearing? Is this what I'm okay, let's continue. We'll come back to this. All right. It improves geometric accuracy relative to physics-based methods, co-folding networks, and deep learning conformer generators, while maintaining broad chemical coverage that extends to small molecules. VLU1 also supports generative applications, enabling the design of novel macrocycles with tailored chemical, structural, and property profiles. So I can assume, for instance, they can design a specific macrocycle that has a specific membrane permeability. Okay. So it's also a generative model too. Okay. Together, these capabilities establish VLU1 as the foundation model for accelerating the development of next generation macrocycle therapeutics. Woo. Let's go. Macrocyclic peptide therapeutics offer the potential to bind to traditionally undruggable protein surfaces, but that's the value proposition here. Or is it? No, this is not a value proposition. But this is the value of a macrocyclic peptide then. A macrocyclic based peptide therapeutics or whatever. Okay, so they offer the potential to bind to traditionally undruggable protein surfaces. Should I explain? Can I explain this? Should I explain this? Okay, give me 1 second. Move on. It's source. Ignore for now because we're not doing updates at the moment. Okay, all right. So basically, right, whenever you take when you take a drug that's supposed to bind to a protein, here's how it works. Let's say you have like this is a cell, right? Actually, oh, this is beautiful. I can like zoom in as much as I want. All right, so let's say this is a cell, right? Now, on the surface of the cell, there are things called receptors. If you zoom in, yep, they're right here. The little things called like receptors and stuff. Right, and this is just a very, very rough example, so like ignore the inaccuracies, please. The receptors aren't actually shaped like this. But like, let's imagine like you have a cell, like a cell, like your nucleus and everything, your mitochondria is all in here, yada 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 yada. Your cell can like do stuff, right? And it can change its internal environment for better or for worse, depending on like the signals it gets from like either like within the cell itself or like from outside the cell. So let's say so let's assume that there's a disease called disease X, right? The way disease X works is that like we have the disease bacteria here. Oh my gosh, you have the disease bacteria here, right? And then the disease bacteria will come down here and then try to bind to this receptor, like a key. So think of this like it's a lock and there's a key. Now the reason why like we have these receptors here is because they're kind of like you can think about them like the receivers, right? So like if you have a TV at home and you have a remote, you know, like your remote works at a certain frequency and your TV receiver is meant to like expect like an input from at a certain frequency, right? For example, like if you use a different remote, it's not gonna work, whereas if you use your own remote, then okay, you're good, right? So you can think about it in that sense, right? Like this receptor expects something of a specific shape, and if the disease entity is in that shape, it can like maybe block or like bind to this receptor that can trigger whatever you want. Now let's say I know that this is like a very like I don't even think this this probably exists, but whatever. This is widely inaccurate. Let's assume, for all intents and purposes, guys, that this receptor, once you trigger it, it's basically a shutdown. It basically tells the cell to shut down, right? So like the entire system here is just gonna die. It's just gonna die. Blah 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 blah. Cell cytoplasm everywhere. Yada yada yada. It's gonna explode. Let's say the way for that to get triggered is by having something bind to this receptor, right? And activating this lock. That's bad. So one way you could do this is to, I don't know, let's say invent our own drug, right? Give me a second. Let's see. Invent our own drug that's shaped like this or something. And then our drug will come here and then just like block off this center, so that whenever this guy tries to come in here, like it can't bind anywhere, and hence it can't trigger this, right? Let's assume that's a case. That's the case. Then voila, you've made a drug. And a lot of drugs are roughly, I mean, they roughly follow this pattern, right? Like they are going to bind to a target and either like inhibit, which is basically like block inhibit this what you call it, the receptor, right? It's gonna bind in but not trigger anything. Or it can like bind somewhere else on the side and then change the shape of the, like, there are different strategies. It's like either you can make something that fits in here but doesn't trigger anything, or you can have something that binds to the side, and because it binds to the side, the shape of this lock is not going to change into like something like this now, right? It's going to change to something like this. And now whenever that disease tries to come in, even though there's nothing in there because it's a different lock, you can't go in. All right. So that's one way you can design meds, right? Now, going back to our paper here, it's saying like microcyclic peptide therapeutics offer the potential to bind to traditionally undruggable protein surfaces. So what I'm assuming they're saying here is that like traditionally, maybe you have like your microcycle. I don't know, like it's something. Well, actually, no, that's too big. Let's zoom in. Let's zoom in. Let's zoom in. Let's assume that our microcycle is something like this. Well, let's actually, yeah, let's use this example. Actually, yeah, that's fine. Wait, no, I said my eraser. That's my eraser. All right, let's assume a microcycle is something like this. I don't know, just imagine like 12 plus n membered ring or whatever, where n is like 0 to infinity. Oh, can't be infinity realistically. Whatever, let's assume this is the case, right? We have our sample here. Let's say maybe in this specific receptor now, other attempts to make a molecule that could go in here didn't work, right? It was like try to come in, bind, didn't work. So what they're saying is microcycles in this case are more, well, not more anything. There are some cases where maybe this guy didn't work, but like you put this guy and everything was Gucci, you know? This is a very, very unpolished, bro. I hope no one like chews my head out for this, because you know, if I try to say this to like a professor, this is basically bonkers, what I'm saying. Well, not, I mean, it's not totally wrong. So that's what I'm understanding, right? Because that's how like drug interactions work typically. Okay, all right, let's continue with the paper. Oh my gosh, they weren't even seeing the thing. Oh, my bad. So basically what I was saying is like, okay, let's say, so this is our microcycle. Let's say this guy is a regular drug, didn't work when you tried to bind it here. This guy, because it's a microcycle, well, I don't know, it has some like greater properties or whatever, binds in here, all right? That may not even be how it works even, but let's see. Since I know they mentioned permeability, so like it goes in, travels into the cell. Whatever, we'll see. Making so many assumptions now. I'm gonna correct them in a bit. All right, let's go back to our paper. I have to be up by like 12. All right, cool. De novo design studies have shown that microcycles composed of canonical amino acids can be engineered with atomic level accuracy. De novo design studies. It's always good to check that you're not assuming what you know. From scratch. All right, cool. About as much. All right, so de novo design studies, basically, studies where they create the peptide from scratch or whatever. Have shown that microcycles composed of canonical amino acids, so I think your 12 amino acids, your 20 amino acids, oh my god, can be engineered with atomic level accuracy. Engineered. What do they mean by that? De novo design studies have shown that microcycles composed of canonical amino acids can be engineered with atomic level accuracy, vastly expanding the set of scaffolds beyond those found in nature. All right. Before I click on these like other references, this is what I'm thinking. Right? So this is what I'm thinking. Let's zoom out here. Let's come here. But let's not zoom out too much. So what I'm thinking is, maybe for instance, we can have like a macro cycle that is like, so L H L H. Oh my god, no, this is gonna form a horrible circle. Give me 1 second. Alright, so L H L H L H L H L H L H. I don't know. Maybe. Oh wait, let me draw the bonds differently. We'll use the color. I don't know. All right. Let's assume. So let's assume that this is an example microcycle, right? We have a leucine, histidine, leucine, histidine, and alternative bases like polar, nonpolar, polar, nonpolar, polar, nonpolar. I wonder if this will collapse on itself and just form like a nice beta sheet structure. All right, whatever. Let's assume this forms, right? So a scaffold would be, you know, maybe you take this and then you say at every 2, 4, 6, 8 position, we can swap it with something else. So basically, like this spot, 3, 4, this spot, 5, 6, this spot, 7, 8. Wait, no. 1, 2, 3, 4, 5, 6, 7, 8. This guy. Let's assume like at 2, 4, 6, and then 8 position, it's free game. We can add whatever, we can substitute whatever you want here. So instead of having like the histidines be there, we can say maybe we can put like phenylalanine or something. Or whatever thing you want. So that's basically you saying, hey, given this like molecule, these positions can be substituted for like whatever you want. That's you making a scaffold. That's you making a scaffold. It's the same way where like gosh, how do I put it? I want to give an analogy, but it's not clicking right now. An analogy for like peptide scaffolds. Like you ever have stencils, right? You know, it's like a big like sheet of cardboard or whatever the material is, and you have like cutouts in there. Right, so like this is a cutout, and then like this is a cutout, right? So and here maybe like, yeah, you can only have like these 2 letters, but like you can make the colors different, right? In that sense, that's kind of what a scaffold would be. I don't know why I'm not getting any of the better terms for like analogies right now, but yeah, that's what a scaffold would be. All right. My god, we're not even going anywhere. Let's see where this. All right. So de novo design studies have shown that microcycles composed of canonical amino acids can be engineered. I don't get what it means by this engineered here. Engineered with atomic level accuracy, vastly expanding the set of scaffolds beyond those found in nature. All right, cool. Okay, we should get to that. Wait, what? Ah, it's a Nature paper. I can show that on stream. Yeah. It's also in Nature Chemical Biology. Accurate design of de novo, accurate de novo design of high affinity protein binding microcycles using deep learning. Anyway, more recently, computational pipelines have been extended to chemically diverse microcyclic backbones and non-peptidic microcyclic oligoamides. Whoa. Nature is okay. This is science. Science open. Fully open. Yeah, whatever. We'll follow up off stream and read. Damn, they try to gatekeep the knowledge. That's crazy. That is crazy. Now, these are macrocycle examples. Sulfur. Alright. Let's gosh, we're still in introduction. Alright, okay, whatever. More recently, computational pipelines have been extended to chemically diverse microcyclic backbones. So computational pipelines, I mean, are we, is this us saying that, I feel like this music is a little bit too loud. Are we saying that we're just adding more diverse macrocyclic compounds to the data set, to the training data? More recently, computational pipelines have been extended to chemically diverse macrocyclic backbones and non-peptidic macrocyclic oligoamides. Okay, what is an oligoamide? Because that also needs to be answered. What is an oligo? A short synthetic or natural molecule made of a few repeating chemical units linked together by amide bonds. Do I trust ChatGPT now? Oh. Neolactum from the leaves of Angolocalix, Angilocalix. Yeah, I'm not reading that. Where's my American? Don't we have like a chemistry Bible or dictionary or something? All right, let's assume this. It's of course it's from the dictionary. Any compound has several amide groups. What? It's like histidine. histidine has like, no, it's not. It's an imine, I think. Imine. Okay. Okay. All right, back to the paper. All right. So more recently, computational pipelines have been extended to extend the chemically diverse microcyclic backbones and non-peptidic microcyclic oligoamides. This chemical diversity opens the possibility for macrocycles to address challenging targets involving both intra and extracellular protein-protein interactions. So basically, like binding to the membrane proteins, or like binding to like a protein inside the cell. What is this funky ass beat though? But it's cool. All right, let's go back to the paper. Okay. All right. Existing methods to predict the structures of macrocyclic peptides are largely derived from tools for protein structure prediction or small molecule conformer generation, right? So before going on, I would assume why, because I know like they're basically gonna say like these methods don't support Villiers 1, right? And I'm assuming I'm making so many assumptions here, but I'm assuming it's because peptide macrocycles have unique properties, just that you cannot just from their shape, that you cannot just like predict with traditional what do you call it, what you call it, structure prediction models. Let's see. All right, existing methods to predict the structures of macrocyclic peptides largely derive from tools for protein structure prediction or small molecule conformer generation. Both have important limitations for chemically diverse cyclic systems. What are the limitations? Both have important limitations. All right, so limitations for, so basically protein structure prediction models have limitations for cyclic systems. So what are the limitations? Generalized structure prediction works. So the generalized structure prediction networks such as Bolt2 and Rosetta Fold 3 can in principle model macrocycles, yet in practice do not generalize well to non-canonical chemistries. And typically fail to produce. Oh, so because like macrocycles are non-canonical chemistries? Hold on. I mean, oh, I guess for peptides, I guess for peptides, like, oh wait, okay, never mind. Nope, we are not doing that. Not on stream, buddy boy. No, not on stream. Yeah, in practice, do not generalize well to non-canonical chemistries, and typically fail to produce sufficiently diverse conformational ensembles for macrocycles that may lack a single well-defined ground state. what do they mean by ground state? Are we talking of, is this something that is thermodynamically related? Like it, this has to be like a thermodynamic related concept, right? Like the ground states. What do they mean by that? Are they saying they don't have like for macrosecs, they don't have a single stable configuration? Like a single stable thermodynamic configuration, right? Because in my head, this is what I'm thinking, right? So let's change this guy to white. Nice. All right, so let's assume this is the landscape, right? And then you have your sequence right here. And then let's make a few holes in the landscape. And then let's actually like make a very non-scientific graph here. And this is energy. Actually, no. This is like stability. Right? Let's say this is just like the length, or like, I don't know, area or length of the landscape. Whatever, some size indicator. The point is like we're trying to go here, right? So for the thermodynamic theory of like peptide, basically peptide folding and protein folding and peptide assembly, I guess, is that your sequence will want to be in the most stable configuration possible. So like it's gonna be oh my gosh, messed it up. It's gonna be folding, but once it hits the most thermodynamically stable configuration, it's going to remain there. That's going to be like the shape, right? So let's say you have like a length of like 50 amino acids, like a peptide of 50 amino acids. It's going to, when it's assembling, it's going to throughout the process, it's looking for the most thermodynamically stable configuration. And once it hits that, then boom, you have your peptide, right? I guess what the paper is saying is that like, because it's saying like it does not generalize well to conformation ensembles for molecules that may lack a well-defined ground state. Maybe what they're saying here is that there's like multiple ground states, right? So like when he has the model to predict, and he's trying to predict along this like very, very, very scientific graph, right? You know, it's not sure if it should go here or if it should go here, because they both seem like very, very stable compared to like the rest, right? That is my assumption on what that statement means. We get more information as we go. All right. Although there are no examples of fine-tuning co-folding networks on structural data for for macrocyclic peptides containing non-canonical amino acids. Okay. These approaches have not demonstrated robust generalization beyond the narrow chemistries represented in their training sets. All right. So let's reread that sentence again. Although there are examples of fine-tuning co-folding networks. What is a co-folding network? My God, I have to really like brush up my protein design knowledge. For macrocyclic peptides containing non-canonical amino acids, these approaches have not demonstrated robust generalization beyond the narrow chemistries represented in their training sets. Right? Okay. Small molecule conformer generators are designed for diversity, but often do not generalize to larger flexible molecules with ring constraints. Okay. Conformer generators. And 3D spatial arrangements. Okay. Alright. Okay. Because you do need the 3D spatial arrangements of your molecule to know if you can bind to a target. I see. Alright. Okay. Alright. Small molecule conformer generators are designed for diversity but do not generalize. So a small molecule conformer generator. If I were to take a guess what this is, because I've never heard of this till today, I'm guessing it's a model. I'm guessing it's a model that in 3D space, let's say you give it like I don't know, let's give it a cyclohexene with a C here, H3 and CH3 or whatever, and you take it, you feed this into the model, and then out you get maybe the X, Y, Z coordinates of like the methyl, and maybe you get like the hydrogens, maybe you get the carbons, and then you get like the ring, yada yada yada. Because when you do this and you get the structure, right? Maybe it's gonna give you like the XYZ coordinates of like these pieces. So I'm guessing that's a conformer generator. That's what I'm guessing. You are welcome to check those, so let us check. Let's ask Google's AI. So wait, so they predict conformational assemblies. They generate a set of energetically stable or alternative 3D shapes. When you run a conformer generator, it typically delivers a 3D molecular file like a .sdf. Oh, okay. I've worked with these files before. Okay, never mind. And an atom block XYZ matrix. Okay, something like this. All right, cool. Not just this, but it's more than vectors. Yes, we know. All right, cool. Okay, all right, where were we? Small molecule conformer generators are designed for diversity, but often do not generalize to larger flexible molecules with the ring constraints. Physics-based protocols that use molecular dynamics or stochastic sampling are capable of modeling highly complex macrocycles, but they are inefficient and their accuracy tends to decrease on larger macrocycles. All right, cool. Let's look at macrocycles here. Let's actually zoom in. Hold on, because I need to see this shit. All right. Lorlatinib. All right, so we got our little tyrosine right here. We got our What is this? Histidine? Oh, this is not. No. That's not histidine. This is histidine? Trying to make out the shapes. Okay. All right. But I mean, either way, they give us the size in angstroms. So 10.1 angstroms. Okay, it's small. It's small. Yes, it's the X-ray structure. Predictor structure. Oh, okay. They're overlaid. Oh. Bro, this image, bro. All right, small macrocycle, tail to tail side chain. All right, this is grizzlomycin, alpha amanitin. It's a bicycle. Okay, cool. I'm assuming this is more complex, and also larger with 0.6 angstroms. Oh, this bad boy is big. Whoa, 0.74 angstroms. All right, so let's see. Figure 1: bioactive conformer prediction and sampling efficiency of Villiers-1. So in image A, examples of bioactive macrocycles for which Villiers-1 predicts conformations within sub-angstrom accuracy measured by the root mean square deviation. Villiers-1 generated structures, green, are overlaid with its corresponding X-ray structures from the. Oh, they're good. Oh, they're good. They're so good. I actually thought it was like just an artistic decision. I didn't even see it. Oh, they're good. They're actually pretty good. They're actually pretty good. I wish they had like better like molecular representation, but let's see. Like I want to see what this compares with, how this compares with the other. Well, okay, let's see something. So 0.1 angstroms. This is like damn near the same. Let me see. Can we zoom in? Like these okay, they're SVG. Bro, God bless these folks, man. Yes, they know what's right. Use SVGs. Actually, I take that back. They're PNGs. Yeah, they're PNGs. Well, I take back my blessings. Okay. All right. So this is 0.1. This is pretty small. And then we go to like, let's actually let's see. Maybe we can find a trend, right? What's the next smallest one? So 0.1, 0.27. It's not, I mean, it's largely okay, like this region and this region right here, like pretty out of sync. 0.27. Let's see. 0.30. Yeah, I mean, it's not too bad. Honestly, not too bad. I want to see like this versus that of the other. Oh yeah, this is the energy landscape. That's what I'm saying, by the way. Oh yeah, the y-axis is energy. It's the total energy. What am I arguing? Oh, yeah. Okay. All right. So this is 0.31. Actually, no, it's 0.3. So yeah, pretty out of sync, well, not as in sync as the others, but like honestly, not too bad, I guess. All right, what's the next biggest one after 0.3? It seems like it's the 0.52, and this starts getting so like with the 0.1 angstrom is really great, really perfect. With this, and especially with this like methyls on the end, or methyls and ethyls. Methyls and oxygens and nitrogens gets out of sync, right? After 0.6, let me see, this is 0.52. 0.6, 0.74. Yeah, I guess not out of sync. Whoa, this is out of sync. And then 0.87A. It's not, I mean, yeah, it's, the rotations are really not that great here compared. But then again, this is compared to like their own model predictions. I wonder how shitty the other methods are, but they didn't show it though. I wonder why. I mean, let's see. Oh, okay, they didn't show it or whatever, but we have the, oh my gosh, yes, Daniel, read. Okay, fraction of macrocycles with ring MSD less than 0.1 angstroms. All right, so oh my god, no, I was misinterpreting the thing the whole time. Oh my god. Okay. Oh my god, this is embarrassing. Okay, hold on. I think it's root mean square deviation. Okay, I got it. Oh, so the smaller than 1 it is, the more similar it is to the target of choice. So these are all good. This is just perfect. Well, not perfect. This is almost 1-to-1. Almost 1-to-1. Okay. And then the most deviated one is this guy. Okay. But even then, like these fraction of macrocycles with ring, bro, this is insane. What? Fraction of macrocycles with ring RMSD less than 0.1 less than 1 angstroms for NMR. I don't understand this. Receptor bound macrocycles. Is it like is the model I mean, it's pretty consistent results like all through. Is the model predicting the conformations while the macrocycle is bound to its receptor targets? I think so. Let's see. All right. This gap motivates the development of new methods specifically tailored to model macrocycle conformational landscapes. Here, we introduce Villiers-1, a deep learning model for generating conformance of macrocycles. Villiers-1 operates on a uniform all-atom representation that does not distinguish between peptide and small molecule chemistries, enabling a single architecture to accommodate the broad range of chemistries encountered in macrocycle design. This representation, let's reread that again. Okay. On a uniform all-atom representation that does not distinguish between peptide, small molecule chemistries, enabling a single architecture to accommodate the broad range of chemistries encountered in microcycle design. This representation simplifies the use of molecular structural datasets and lets the model learn generic structural principles governing both polymer and non-polymer molecules. Villiers-1 is trained on an extensive set of internal and external structural datasets spanning diverse topologies, chemical classes, and molecular sizes across a broad suite of benchmarks. So Villia 1 is learning from first principles. Okay. Villia 1 substantially outperforms existing approaches in sampling experimentally. Villia 1 across a broad suite of benchmarks. Villia 1 substantially outperforms existing approaches in sampling experimentally observed macrocycle structures, nearly doubling the success of accurate ring reconstruction with an RMSD of less than 1 angstrom, relative to the leading physics-based models, and markedly exceeding the performance of co-folding networks, particularly for molecules containing a non-canonical amino acid or non-peptidic fragments. We show the utility of accurate structure sampling on 3 real-world applications: as a foundational model for downstream property prediction, as a sampler for conformational landscape analysis, and as an oracle for designing novel topologies. As a property prediction model, Villia 1 is capable of learning from internal assay data to predict key drug-like properties that enable oral bioavailability. Okay, as a property prediction model, it's capable of learning from internal assay data. Okay. That's by the model not being trained for binary discrimination. Okay. Finally, as part of a generative pipeline, Villia 1 is capable of scaffolding motifs from larger macrocycles into smaller ones. Oh, this is optimization here. Oh yeah, it is. An important problem in hit optimization of drug-like microcycles. Taken together, these results demonstrate that Villia 1 is a general-purpose model capable of aiding in all stages of designing and optimizing macrocyclic peptides in real-world drug discovery campaigns. Okay, so take the graph, take the 1D features, take the 2D features, and a feature embedder. The architecture is inspired by an existing work on scaling large transform. Okay, they use a transform. I'm like, there's no way, because they're trying to do atom-atom representation. He's not doing like a transformer on a GNN, on a graph-based network or whatever. As input, the model receives a complete chemical description of a molecule in 3 different modalities: atom level scalar features. Okay, so like maybe what do you call it? For example, the nitrogen atom, you can take like its polarity, its charge, its valence, and all that stuff. But like you have to be careful what you select, right? Pairwise scalar features and atom level vector features, aided by specialized NVIDIA Q equivariance kernels. The core architecture is built on top of components introduced by Jumper et al. in 2020. Triangle attention and multiplication with pair bias. Well, okay, what is triangle attention like? I do not care. I'm not saying it. I gotta read this. In any 3D structure, the distance between 2 points I and J is constrained by the relationship to any third point K. Okay, cool. AlphaFold doesn't just know this, it uses layers specifically built to perform this triplet reasoning. Okay, the layer is the... Bro, this feels like AI slop. What is it? I don't know. Maybe because, you know what, let me stop calling it slop because I don't understand it. The triangular self-attention layers are the computational heart of the performer. They are specifically designed to treat the 2D pair representation grid as a graph, where the attention mechanism enforces the geometric consistency, specifically the triangle inequality, required for 3D structures. Is this a way to preserve 3D information into embeddings? Okay, all right. We'll just go with that, and we'll finish reading that later. Hold on. I feel like we can. Let's see if we can like build this. The model differs from so let's look at this arc. You know what? Let's see what time it is. It's 11:37. I gotta hurry up and skedaddle. All right. Let's see. We'll finish this when we come back. I want to understand this and not just like skim through it like I'm doing Jack. All right. Okay, so feature embedder, you take the 1D features and 2D features, make a pair representation, make an atom representation. So you have two sets of embeddings, right? Update the pair representation as you're updating the atom representation. And so when they say atom representation, what do they mean here? Are they talking about like the position in 3D space? Is this where the triangle attention is being used? So you embed. Okay, cool. Update. Prediction head. So predicted coordinates. Predicted distogram. The hell is a distogram? Did it say wait, am I tripping? Like it said distogram, right? Predicted distogram. Distogram. No. So from understanding, okay, take 1D features, 2D features, represent them in embeddings. You have the atom representation, which right now I am assuming that this encodes some 3D information using the triangle transformer, triangle attention, right? And then you represent whatever the hell this is here. You update these two sets of embeddings as you're doing your training, and then you have your prediction. Well, yeah, obviously, and then you have two prediction heads. One that gives you the coordinates, and so you know by coordinates you can then make the .sdf file because you can generate the representation in 3D space, and then whatever the distogram is, I don't care about that. So this diffusion process, though, what does this do? Conditioning of embeddings, time steps, diffusion coordinate, diffusion process. All right, let's see. Oof. The model differs from popular protein ligand co-folding architectures in three main ways. First, the diffusion process runs through a single unified transformer architecture. All right. As our goal is to explicitly model an ensemble of conformations, we hypothesize that having separate trunk and diffusion models may reduce the diversity of sampled coordinate structures. Second, because let me not just rush that. I think I understood that. The model differs from popular protein ligand co-folding architecture in theories. Okay, so the first way, the diffusion process runs through a single unified transformer architecture. So difference number one transformer block. Okay. As our goal is to explicitly model an ensemble of conformations, we hypothesize that having separate trunk and diffusion models may reduce the diversity of sampled coordinate structures. Okay, so by having separate trunk and diffusion modules, oh my goodness, stop. Trunk module and diffusion modules. Second, oh god, I don't want to skip past that one right now. Time. You know what? It's cool. Second, because we aim to model a broad diversity of non-canonical chemistries, we embed all molecular inputs at the level of individual heavy atoms. Okay, so because we aim to model a broad diversity of non-canonical chemistries, we embed all molecular inputs at the level of individual heavy atoms. Heavy atoms? Are they saying like non-hydrogen atoms? Because realistically, that's gonna be the heavy stuff, right? Like carbons, oxygen, nitrogens, chlorines, fluorines, sulfurs, whatever. While explicitly grouping atoms in canonical residues together in a single embedding is computationally efficient, it limits the generality of the network. Okay. I'm gonna reread this. Oh my gosh, I need to reread this. Okay. Finally, we only input features that describe the chemical structure of the input molecule. So we only input features, okay, that describe the chemical structure of the input molecule and omit auxiliary features like molecule type, atom name, okay, or positional encoding. Positional encoding. What? No. We omit auxiliary, so we only input features that describe the chemical structure, such as bonding, bond length. Is that one? And omit auxiliary features like molecule type, atom name, or positional encoding. Okay, we'll get to that. We reason that having only chemically relevant features will make the model less likely to memorize training data and more likely to generalize to novel molecules. Fair. We extend Villiers-1 architecture with two downstream models, a confidence model and a property prediction model. Both downstream models share the architecture of the conformer generation model and are fine-tuned from its weights. Both property and confidence models take in the same features as the base model, in addition to the structure of a generated conformer. All right, 2 points. So I think, you know what? I'm glad I picked up this paper. Let's see how the best in the world are doing their modeling. Could I take some things out of this? I mean, definitely. Like, I love what they're doing here. Data gathering, though. How do they gather the data? That is, let's see. All right, so we're in section 2.2. I gotta head out because, like, you know, I have to go do some other stuff, do some studying somewhere else. But Yeah, hopefully we're able to take something out of this stream. I'm gonna revisit my analogies again. I promise I'm gonna have better analogies next time, because I feel like that TV remote analogy did not hit. It did not hit, bro. But okay, all right, we'll do this again.